Dear students, let me welcome all of you to the session on expansions of functions. Actually, the content of this chapter is Taylor series and Maclaurin series. The Taylor series and Maclaurin series helps us to express certain functions in a form of a series. In order to get that series representation, there are loads of assumptions on the functions. And they are, the first one is the expansion of the function in ascending powers of the variable is possible. First of all, we have to obtain a series representation, and first thing that such a representation is possible. Another assumption is all the higher derivatives of the function exist and finite. Okay? Higher derivatives must exist. Then only we can discuss about Taylor and Maclaurin representations. Another thing is this, an infinite series. The infinite series must be a convergent series. In your previous classes, you have seen that there are so many series which converge, and also there are series which do not converge. For example, if we consider the series 1 plus 1 plus 1 plus etc., it is a divergent series. At the same time, if we consider the series 1 by 2 plus 1 by 4 plus etc., then it is a convergent geometric series with a common ratio 1 upon 2. Okay, so here also we have to take an account of so many things. They are theoretical concepts, and you will study such concepts in detail in real analysis class and some other calculus class. So in this session, our aim is to find the Taylor series representations and also Maclaurin series representations, so that I do not enter into the theory much. I concentrate on finding representations for a given function. For that purpose, what we do is we define Taylor series of a function f. See, f is a function, okay, and we discuss about the Taylor series of f at the point x is equal to a. At the point x is equal to a. Okay? And that is defined as, the left hand side is enough. The left hand side gives us a very compact form. Okay? The left hand side says that we have the representation summation k is equal to 0 to infinity fk of a by k factorial times x minus a to the power k. What is fk of a? Fk of a denote the kth derivative, the value of the function. Which function? The function which is the kth derivative of f. Fk of a. See, fk of a is, you note this point, fk of a is the value of the function fk of x evaluated at x is equal to a. Okay, so what we do is we first find the kth derivative of the function f, then evaluate the value of that function when x is equal to a. Okay, so look at the left hand side once again. When we put k is equal to 0, what happens? when we put k is equal to 0, we have f0 of a by 0 factorial times x minus a to the power 0. Okay, you all know that 0 factorial is regarded as 1, x minus a to the power 0 is again 1. And now what about f0 of a? f0 of a means no derivative is applied, no differentiable derivative operator is not applied on the function f. Okay, that means f0 of a is the value of the function f of x evaluated at x is equal to a. Evaluated at x is equal to a. Okay, so that is the reason why we put a f of a here on the right hand side. Okay, then you put a k equal to 1, what happens? Then f1 of a, f1 of a means we find the first derivative of the function f of x, then evaluate it at x is equal to a, which we denote as f prime of a. We also call it as f dash of a, and I call it f prime of a. Okay, and what about 1 factorial? 1 factorial is 1. Okay, x minus a to the power 1 is x minus a itself. So we get the second term, isn't it? You got the point. Now what will be the third one? Naturally we put x equal to 2. Okay, then what we get? X minus a whole square by 2 factorial times f double prime of a. What is f double prime of a? F double prime of a is the value of the function f double prime of x evaluated at x is equal to a. What is f double prime of x? F double prime of x is the second derivative of the function f of x. I think you got the point. We continue this process. This is not an ending process because we are considering an infinite series, so we continue this process. Okay, and for convenience, we assume that the series converges. Okay, there are so many conditions to say that the series converges. For example, we have already mentioned that we have mentioned 3 conditions. Okay, only if these 3 conditions are satisfied, then only we can say about the continuity. We can discuss about the convergence. So for a moment, we assume that the series converges and we continue the process. Okay, so it is your duty to keep in your mind this formula. This is known as the Taylor series at x is equal to a of the function. Okay, and naturally, see in this step you can see the right hand side is just the expansion of this compact form. Okay, summation k is equal to 0 to infinity fk of a by k factorial times x minus a to the power k is a compact form, and we have expanded, and the expansion is given on the right hand side. Okay, usually we say that the Taylor series, see in your memory you can either keep the compact form on the left hand side or keep the one on the right hand side, no problem. Okay, then what we take is this: we consider that series as the Taylor series of the function f of x at x is equal to a, and naturally we denote it as f of x is equal to f of a plus x minus a times f prime of a plus x minus a whole square by 2 factorial times f double prime of a plus etc. Okay, I think I request you, all of you, to keep this formula in your memory because we need this formula to do lots of problems. So this is an extra plus etc., and we can, if we write the nth term, it will be like this. Okay, see, this is plus etc. plus this is the nth term. What is the nth term? X minus a to the power n minus 1 by n minus 1 factorial times f n minus 1 of a plus x minus a to the power n by n factorial times fn of a plus etc. Okay, and this is a polynomial. Next one is we consider a polynomial. What about this polynomial? This polynomial is this. You look here. You can see that up to the first nth term, they are parts of the Taylor series mentioned here. Okay, and after that, we do not continue the infinite series representation, and instead we simply write an expression x minus a to the power n by n factorial times fn of a. And we do not continue the process, and we stop here. And if we stop this n plus 1th step, then it becomes a polynomial. It becomes a polynomial. Okay. See, what we do is we only consider the first n plus 1th terms of the series. We only consider the first n plus 1th terms of the series. And we consider it as a, then it is not a series. Okay, it is a finite sum. You see, the right hand side here is a finite sum. Okay, and what about this finite sum? You can see that everywhere there is a presence of x. X is a variable, an unknown, and here x minus a whole square, etc. The last term, there is a term x minus a to the power n, x minus a all to the power n. What about x minus a all to the power n? On expansion, x minus a all to the power n gives us a polynomial of degree n. A polynomial in the variable x of degree n. What about x minus a to the power n minus 1? It gives a polynomial of degree n minus 1. So, by looking on the right hand side of this representation, you can see that on simplification and on expansion, the right hand side gives us a polynomial of degree n. Polynomial in the variable x of degree n. And that polynomial is called the Taylor's polynomial of degree n. Okay. What about what is the difference between Taylor series and Taylor polynomial? Taylor series is an expansion in the form of a series, and we take only the first n plus 1 terms, then it becomes a polynomial, and that polynomial is called the Taylor polynomial. Yeah. So, in certain situations, instead of x, sometimes we prefer x plus h. Okay. That means we replace everywhere. X is replaced everywhere with x plus h. And this is also a form of Taylor series. Instead of a, you can see here. See how to get this one. Instead of x, we take x plus h. Okay. And what about a then? A becomes, instead of a, we get x. Okay, this is x plus h, this is x, and instead of x minus a, we get h. So this is another alternate form of Taylor series, and this series also will be helpful to do some problems, and we will discuss this when the situation arises. We consider an example. First one is an example. Expand log x in ascending powers of x minus 1 as for the term containing x minus 1 to the power 4. Read the question carefully. We have to express log x in ascending powers of x minus 1. That means we have to express log x as something times x minus 1 to the power 0 plus something times x minus 1 to the power 2 plus etc. up to something times x minus 1 to the power 4. That means we are not asked to find the Taylor series, but we are asked to find the Taylor polynomial of degree 4. See, here we are asked to find the Taylor polynomial of degree 4. Okay. So, what we do is we write like this. With a is equal to 1. Here we have to write the series in the form of x minus 1, isn't it? So we look here. Here you can see that you can either look at the Taylor series expansion or you look at the Taylor polynomial expansion, no problem. For convenience, I look at this Taylor polynomial expansion because we only need to find the fourth term and then etc. We will add plus etc. to get the series, isn't it? So if we look here, the polynomial, here a is, instead of x minus a, we have x minus 1. That means our a is 1. A is 1. So we first note that point. A is equal to 1. Okay. Then you look at the formula. You can look at either the polynomial. If you look at the polynomial, then we get a polynomial of degree n. But here we have to express log x in ascending powers of x minus 1 for the term containing x minus 1 to the power 4. So what we do is, we consider this one or this one. I prefer this Taylor series. Okay, so here f of a becomes, what is a? F of 1. X minus 1 is here. F prime of 1. F double prime of 1, etc. So we have to find out all those things. So we write a equal to 1. Okay. Then what about f of x? F of x is given that log x. Then what about f of a? F of a is, see, we need f of a. What is f of a? F of a is f of 1. F of 1 is log 1. Log 1 is 0. Because we are considering natural logarithm unless otherwise specified. So log 1 is 0. What about f prime of x? We know that the derivative of log x is 1 upon x. So f prime of x is equal to 1 upon x. So its derivative is, f prime of x is 1 upon x, and we evaluate f prime of a. F prime of a. What about f prime of a? F prime of a is, what is a here? F prime of 1. Here a is 1. So what about f prime of 1 then? 1 by x. In the place of x, we have to substitute x is equal to 1. So we get 1 by 1 is equal to 1. So we get this answer. So in the second step, we find f double prime of x. What is f double prime of x? F double prime of x is the derivative of 1 upon x. Derivative of 1 upon x is negative 1 upon x square. I think you are familiar with such basic differentiation formula. Otherwise, you must quickly review those things by looking your previous year textbooks. D by dx of, you have a formula here, d by dx of x raised to n is equal to n times x raised to n minus 1, and this formula is valid only when tell me, there is a requirement. What about that one? So this is a formula. So by here we have n is equal to 1. N is equal to negative 1. So here negative 1 to the power x to the power negative 1 minus 1, which is negative x raised to negative 2. So we get negative 1 by x square. So we evaluate f double prime of x at x is equal to 1. Here instead of x we have to write 1 here. F double prime of 1 is equal to negative 1 by 1, which is equal to negative 1. Okay. Next we find f double prime of x. What is f double prime of x? F double prime of x is f triple prime of x. What is f triple prime of x? F triple prime of x is nothing but d by dx of negative 1 by x square. That is equal to negative 1 times d by dx of x raised to negative 2, which is equal to negative 1 into negative 2 into x raised to negative 3. So negative 1 into negative 2 becomes 2. X raised to negative 3. We can write it as 2 times 2 by x cube. 2 by x cube. And we evaluate that function when x is equal to 1 and we get it as 2. Now fourth derivative of f is the derivative of 2 by x cube, and that you can see here, that is d by dx of 2 by x cube is equal to 2 times d by dx of x cube. That means negative 3 times x raised to negative 4, which is negative 6 times x raised to negative 4, and we get this answer. 6 by x raised to 4. 6 by x raised to 4. Here 4 is required. So, fourth derivative of f evaluated at x is equal to 1 is negative 6 by 1, which is negative 6. Now we substitute all these formulas, all these values in the Taylor series expansion. And what is the Taylor series expansion? F of x is equal to f of a plus x minus a times f prime of a plus x minus a whole square by 2 factorial times f double prime of a plus etc. plus x minus a to the power n plus 1 by n minus 1, plus x minus a to the power n minus 1 by n minus 1 factorial times f of n minus 1 a, means it is the value of the function fn minus 1 of x evaluated at x is equal to a plus x minus a to the power n by n factorial times fn of a plus etc. We continue this process. Okay, this is a series, and if we finish at this end position, we get a polynomial. But here we have to find a series, so we continue this process by putting 3 dots, and we have log x is equal to 0 plus x minus 1. Why here we have 0? Because here we have f of 1 is equal to 0. Yes. Second step is x minus 1 into f prime of 1. What is f prime of 1? F prime of 1 is 1 plus x minus 1 all square, x minus 1 square by 2 factorial times f double prime of 1. What is f double prime of 1? F double prime of 1 is negative 1. So we put it here, negative 1. Similarly, the other one is 2, negative 6. And on simplification, we get log x is equal to x minus 1 minus x minus 1 all square by 2 plus x minus 1 all cube by 3 minus x minus 1 to the power 4 by 4 plus etc. Okay. This is the Taylor series expansion of the function log x. We have to put 3 dots here. Okay. This is very important. If we finish here, we can call it a Taylor polynomial associated with the log x. Then we cannot write that log x equal to that polynomial, because we have found only finite number of values. Okay. Next is a very simple example. So I just quickly go through it. I think you can follow the steps. You go with me. If you listen with me, then you can follow the steps very easily. Here f of x is e raised to x, and we have to find the Taylor series and Taylor polynomials. Okay, both here in the question there are 2 requirements. First one is Taylor series, and another thing is Taylor polynomials. Okay, so we write f of x is equal to e raised to x is the function, a is equal to 0, and we have to apply the polynomial formula and the series formula mentioned so far. For that purpose, what we do, we first write down f of x, then evaluate f of 0. Why we find f of 0? Because we have to find f of a. We have to find f of a. What is f of a? F of a is, here a is 0, so f of a is f of 0. What is that one? That is e raised to 0. What is e raised to 0? E raised to 0 is 1. So we get this term. Now next we find f prime of x. We know that the derivative of e raised to x is e raised to x itself. So f prime of x is e raised to x. And what about f prime of 0? What is f prime of 0 means? F prime of a, that is equal to f prime of 0, which is equal to again e raised to 0, which is equal to 1. Then we find the derivative of e raised to x, and it is f double prime of x, and it can be seen that f double prime of 0 is equal to 1. And if we continue this step, even after any step, the value will be derivative will be e raised to x and the value will be 1. So the Taylor series of f at x is equal to 0 is, see, by looking at the formula here, it is actually f of a. When we put a equal to 0, it becomes f of 0. Here actually f prime of a times x minus a by 1 factorial. Here a is equal to 0, so we put here. Second one is f double prime of 0 by 2 factorial times x minus 0 square plus etc. We continue this process. So what we get is, by substituting these values, what is f of 0? F of 0 is 1, so we put here. F prime of 0 is 1, so we put here 1. X minus 0 is x, so we continue that. So we get this one. This is known as the Taylor series expansion of the exponential function. And this series has a special name, and that name is exponential series. Exponential series. E raised to x is equal to 1 plus x square by 2 factorial plus x cubed by 3 factorial plus etc. plus, we stress the nth term, n plus 1th term. What is the n plus 1th term? X raised to n by n factorial plus etc. It is an infinite series. This is a convergent series, and we will learn it later that this is a convergent series for any value of x. Okay. This is also, we will later see in the chapter that this expansion e raised to x is equal to 1 plus x square by 2 factorial plus x cubed by 3 factorial plus etc. plus x raised to n by n factorial plus etc. is also called a Maclaurin series for e raised to x. The reason will be clear to you when you continue the session. But to get the Taylor polynomial of degree n, what we do is, we finish at x raised to n and we do not write plus etc. We stop here. There is no terms plus etc. We stop here. So we get 1 plus x square by 2 factorial plus x cubed by 3 factorial plus etc. plus. This is a polynomial x raised to n. We finish here because we are asked to find a Taylor polynomial of order n or degree n. So in order to get a Taylor polynomial of degree n, we have to list out first n plus 1 terms. We have to list out first n plus 1 terms. Okay. Next we have to find the Taylor series expansion of cos x. As in the previous problem, you can see that f of x is equal to cos x, and f of a, what is a here? 0. F of a equal to f of 0 is equal to cos 0. What is cos 0? Cos 0 is 1. F prime of x is equal to negative sin x. So f prime of a is equal to f prime of 0 is equal to negative sin 0 is equal to 0. F double prime of x is equal to negative cos x. That is f double prime of 0 is equal to negative 1. F triple prime of x is equal to sin x. F triple prime of 0 is equal to sin 0 is equal to 0. Sin 0 equal to 0. So in general, you can see that if we find the even derivative and evaluate the value at x is equal to 0, it will be negative 1 to the power n. And when we find the 2n plus 1 the derivative and evaluate at the function, evaluate the function at x is equal to 0, the value will be 0. Okay. So this is very important. This is very important. Very, very important, because while solving these trigonometric type problems, cos x, sin x, etc., we have to write a general form expressions like this. By looking at the general form expansion, we have general expression. You can see that we are, what about f2n of 0 means we are finding the derivative of the function f 2n times, okay, then we get a function and we evaluate the value of that function at x is equal to 0. Okay, here we say that value is negative 1 to the power n. You can observe by looking at this, okay, because whenever we have even derivative, when we find even derivatives, we have always one, sometimes negative 1 and so on, and the value whether it is 1 or negative 1 depends on n, okay, because f2n of 0 is negative 1 to the power n. When we put n is equal to 0, that means this is just f of 0. F of 0 will be, when we put n is equal to 0, what will be? F of 0 will be negative 1 to the power 0. What is negative 1 to the power 0? Simply 1. What is f2 of 0? f2 of 0 we have already evaluated here. What is f2 of 0 based on this formula? f2 of 0 will be negative 1 to the power 1, because 2 is 2 times 1. So n is 1. So negative 1 to the power 1, which is equal to negative 1. And whenever we find the odd times, we find the derivative of f odd times and evaluate the value of the so obtained function, the value will be always 0. Okay. So by looking here, you note that you can list out certain values then by looking this formula. That will be good for a level student. See, you can see that f of 0 will be negative 1 to the power 0 is equal to 1. F prime of 0 will be, no doubt, it will be 0 because 1 is odd. Here whenever 2n plus 1 is odd. Whenever we have odd derivative, then the value of that so obtained function evaluated at x is equal to 0 is 0. So no doubt we can simply write like this. What about f2 of 0? f2 of 0 means second derivative. f2 of 0. So here we have to look here. 2 is 2 times 1. So n becomes 1. So here we have negative 1 to the power 1, which is equal to negative 1. Okay. Now what about f3 of 0? There is no doubt because 3 is odd. So without any discussion, we can simply write f3 of 0 is equal to 0. What about f4 of 0? f4 of 0 is, what about 4? 4 is 2 times 2. So this will be negative 1 to the power 2, which is equal to 1. What about f5 of 0? f5 of 0 is equal to 0. f6 of 0, you can see that it is equal to negative 1 to the power 3. Negative 1 to the power 3, which gives negative 1. Okay. So we substitute all these values in this Taylor series expansion and we get f of 0 is 1, f prime of 0 is 0. Okay. So we continue this step. What about f2 of 0? f2 of 0 is negative 1. So we get this step. Second, another step, next step is 0. Then the next step is x raised to 4 by 4 factorial plus etc. We have this is what about this step? Take care of this step. We have written negative 1 to the power n x to the power 2n by 2n plus 2n factorial. That means we have considered the general term as the term where x has the power 2n, x has even power, because if whenever x has odd power, all the values will be 0. Only x has odd even power have terms, either it will be negative 1 or 1. So the general, we can write it in a compact form like this. Summation n is equal to 0 to infinity negative 1 to the power n x to the power 2n by 2n factorial. And this series is called the cosine series. When we write this, This is known as the cosine series. Verify. And this is also, we will see later that this is also the Maclaurin series. And here we have asked to find the Taylor polynomial, isn't it? The Taylor polynomial we write like this formula. We stop after a stage. So here we finish with up to negative 1 to the power n, x to the power 2n by 2n factorial. We do not write plus etc. Okay. So this is known as the Taylor polynomial. See, you take a caution here. This is not a polynomial of degree n, but a polynomial of degree 2n. This is a polynomial of degree 2n. This is a polynomial of degree n. Degree 2n, because here we have x to the power 2n. Okay. So let me wind up this session today. Okay, we can continue this session again another day. Okay. Thank you for hearing my session. Thank you all.